Okay, so when we finished off, we calculated some correlations, and we also described how correlations were kind of normalized in that there was we divided by both the standard deviation for x and the standard deviation for y, and in fact this means that correlations are between -1 and 1. Let's just get it into red. And we could actually write that as R, the correlation is a member of the interval -1 to 1. So let's kind of go back a little bit and let's kind of go back to our original little graphs. And let's just think what sort of correlations these will actually provide. Since we already have a lot on this, a lot of ink on this slide, we're going to do this in blue. So this perfectly positive correlation would be an R of 1. This perfectly negative correlation would be an R of -1. This kind of blob here, we don't know it's exactly 0 because there's no real pattern, but I'm going to say it's kind of going to be approximately 0. It could be slightly positive, it should be slightly negative. And this correlation here is going to be positive, but it's going to be less than 1. I'm going to look, that's going to be pretty high. That's going to be around maybe a 0.7 or 0.8. So I'm going to say R is greater than 0, and here R is less than 0. This one, it doesn't look like we have much correlation. In fact, there's a curvilinear. There is a relationship, but it's a curve. But again, R is going to be relatively close to 0. I'm not going to put it equals 0. I'm not quite sure exactly what it would be, but there's little or no actual linear correlation there. Okay, so to help you learn a little bit more about the inference in correlations, we have a little game called Guess the Correlation. So usually I challenge my students to it in class, but since we don't have a class, I'm just going to have to be on my own and play it on my own. Oh, I've already used that username before. Hello, Ashliaf. So I'm going to guess this one here is probably virtually 0. It's maybe a little bit of a correlation, but here we go, 0.14. This was a difficult because it's got a few outliers, but I'm going to guess it's still a reasonable correlation. Ugh, this was a hard one. Oh yeah, I'm on a roll here. This one again is going to be very similar to the last one. And in fact, I'm just going to stop there because I want you to think that I'm competent. So I'll let you play around with this. I've never had a run as good as that before, so I think I'm just going to quit where I'm ahead with guess the correlation. Okay, a few other things when we talk about correlations is that correlation does not necessarily mean that we have some sort of causation. When you do structural equation modeling class, maybe when you do some of the stuff on mediation and moderation models with Dr. Landers, you'll think a little bit more about causation. Here for us, what causes what is merely more about common sense. For example, the tweet rate per hour is the social media buzz before a movie is released, and it's probably going to be some way positively, it's going to be some sort of positive pre-indicator of the movie revenue the open weekend, which comes later. So it would generally make sense that that's X and that's Y. But just because two things have a high correlation doesn't mean that one causes another. So there's all sorts. If you go to tylervigeland.com, spurious correlations, um, there's a load of silly things here. So this is like there was a meme a while with a video called Dumb Ways to Die on YouTube. You can search it. And it peaked around 2013. And then we have the number of electronics engineers in Utah. Obviously, that one's not actually grounded at 0, but you can see there's a similar pattern. That's kind of highly correlated. It's got a correlation of almost 1. And we've got customer satisfaction with CVS and regular season assists. You get the idea. Population of memes. There's a load of fun ones which are probably a little bit later. Uh, Popularity of the first name Keelan with automotive recalls for airbags. Butter consumption versus the correlation of epidemiologists in Colorado. Some of this is actually, there may be some, we think about this when we think about partial correlation later. There may be some underlying latent variable because it could be with these that the actual, oh, this is actually per capita. But you can see that butter, you've got two things that are naturally increasing, butter consumption and also the number of epidemiologists. What I was going to say is some of these, um, you've got two things, and there's maybe a third latent variable. So if you had things like car sales and you had things like number of hospital visits, as the population increases, obviously both of those are going to, there's going to be some other relationship, but there's going to be some inbuilt correlation to due to be going up with population. And here we go, another one. Searches for Never Gonna Give You Up, Rick Astley, with Who is Elon Musk. So the idea is if you have a lot of data, so with searches like this, you've got almost infinite possibilities. You can basically data mine until you get high correlations. So it's almost kind of a combination of spurious correlation with this kind of type 1 error. You know, if you do enough combinations, you're going to get some significant correlations here. Okay, I think I'll let you um, explore these things. And if you look at this guy's, theory, he has 25,000 variables and 600 million correlations, and then just basically does data mining, data dredging, where it finds kind of significant values out of those 630 million correlations. So that's kind of interesting. Some of the things I talked about, the confounding variables such as population, or things go down during the pandemic. Lots of things went down during the pandemic, which aren't necessarily related. Truncating of y-axes, um, observations not independent, data dredging. So there's kind of quite, a low end. If you only have a few points, then you're liable to, you can actually get kind of quite significant correlations. If you've got two things that are going up over a few periods of time, then that would give us a significant correlation. So, and you can actually download this guy's Python code. Okay, so that's enough fun with correlation guessing games and spurious correlations. It's back to the math. So, where were we? Oh, we were talking about z-scores. So remember I said that a correlation is really positive if a value is above the mean, if both values at x and y are above the mean, and negative, or if they're both below the mean, or it's negative if one's above and one's below. And that's almost kind of symptomatic with z-scores. When we define z-scores, the z-score is a standardized variable. The first thing we do is we actually subtract the mean, and we divide by the standard deviation. And what do we do in correlations? We also divide by the standard deviation. So I'm just going to give you an example from the book. Now I'm going to convert it. The book example, you can check it's formula 9.2 in the book. I can't remember what page that's on, but formula 9.2, you should be able to find it. They use the population, which is a bit weird because they also use R, which is the sample correlation. I'll have words with the author like that. You should either use the population in sigma, sorry, the population and rho, or you should use the sample and R. But let's just do it with R and do it as a sample. So if we have this, so we have a formula here, and I'm just going to show this formula is actually correct by showing it's the actual, what we defined before. So I'm going to say we're going to go for each of our points. We've got some z-score. You remember what a z-score is? It's the mean divided by the standard deviation, divided by, as this is a sample, it will be divided by n minus 1. That's going to be equal to I equals 1 to n, and then it's going to be x minus x bar divided by S y. So let's just do, yeah, as we're doing I, we really should put the I in. So ZX I, ZY I, and this should be another issue of the book. I think I'm just going to have to go and give this author a piece of my mind, particularly as he condescended me from being in a business school. So YI minus Y bar, also divided by S, and this would be SY, and this would be SX. So if you see what I've done here, this is basically just the z-score. X minus X bar divided by S. Y minus Y bar divided by S. Or divided by N minus 1. Which we can rearrange. This is in the bottom, so we can actually just move that to the bottom. So we could do Y I equals 1 to N. X minus Xi minus X bar. Yi minus Y bar. All over N minus 1. Sx, Sy. And remember, this is what we proved before. We actually had this formula here, and then I kind of, wrote out the two standard deviations and put it in that kind of sum of squares formulation. So equals as before. This is the definition for the correlation. Okay, so let's just, we've kind of finished with the calculation, and this is what we kind of explained before. So this was the correlation can be written as the sum of squares xy divided by the square root of sum of squares x and the square root of sum of squared y. So again, just go back. This was just the calculation that I gave you before, that this is the correlation. And these are just the alternative ways. I think we mentioned this when we did at the beginning. These are just the alternative ways of writing standard deviations. If you want to prove that these two are equal, then you can play around with the math, or you could maybe ask ChatGPT. But this is kind of relatively easy to prove that these are, the left and the right are exactly the same things. Okay, so we move on. One thing before we do the actual statistical testing is I did put together a spreadsheet, and that just kind of gives a few simple examples of correlations. So this is simple correlation examples. And the idea is the first one is just a very simple example of, similar to the one in the slides, of advertising versus sales. As advertising, we've got it plotted here, X and Y. X is advertising, Y is sales. Generally, these go up together, but it's not a perfect relationship. So we can see that the correlation is 0.9. I've actually drawn a regression line on it. And we'll talk about this more when we do regression, but regression, the model fit is the squared correlation. So the square of 0.903 is 0.1867. And if we're doing regression, it gives us a format of the line. Again, we've not covered regression yet, but I'm sure you've come across it. So this would be an actual perfect fit where we have a perfect correlation. You see the correlation is 1. In regression, we have a slope of line of 1 and basically y equals x. So advertising 1, 2, 3, 4, 5, sales 1, 2, 3, 4, 5 gives us a perfect correlation. Even if we shift this, so if we have advertising of 1 is sales of 3, advertising of 2 is sales of 4. So we've basically, it's basically 2 plus x is the equation of y. We still get this perfect correlation of 1. If you see what I'm doing with each of these, basically I calculate the sum of squares for xy, which is the sum of x minus x bar times y minus y bar. I also do the sum of squares for x squared. kind of the sum of squares for x, sum of squares for y, and then the correlation is just sum of squares xy divided by the square root of sum of squares x times the square root of sum of squares y. So I'm just literally using these formulas here. Okay, so back to my little spreadsheet. So next we multiply, and here again, so this time we've got advertising of 1, 2, 3, 4, 5, and we've got sales of 5, 10, 15, 20, 25. And we actually have, again, you can see that the sum of squares xy is much bigger because x times minus x bar times y minus y bar is much bigger. But the sum of squares y is actually much bigger to compensate. So we still get a correlation of 1. So kind of scaling one of the variables, as long as everything is on this line and there's no error, then the correlation is going to be 1. Now this is funny because we have a straight line here and we actually have an error for the correlation. And that's because we have our sum of squares xy is 0 because y minus y is always y bar, so y minus y bar is always 0. So the correlation has a divide by 0 on the bottom. So actually the correlation is undefined here. It's not a correlation of 0. This is in fact an undefined correlation. If we had a line with things jumping, points kind of above and below as well, then we would have a 0 correlation. But here we actually have error correlation. That's just saying if we have the negative version, we actually have a correlation of -1. So it's the reverse, but because x minus x bar is always the opposite of y minus y bar, because they go up and down together, then the product is always negative. So SXY is negative, so the correlation is -1. Here we've got, we would imagine we'd start off at 6 for sales revenue with advertising of 0, 5, 1. So the equation is y equals 6 minus x. And the r squared is 1 because if the r is 1 minus 1, you square it and you get 1. And this is our friendly movie example. Again, we calculate the correlation here is 0.9, just over 0.9, which is quite a strong correlation. You see our regression line and you see the points, they go up together. Now notice the our errors get bigger as our tweets per hour get bigger. This is called heteroskedasticity, but we'll talk more about that in the regression chapter. So do play around, and again, just playing around with the Excel formulas should help you understand things a little bit better. Okay. So we've just done the tweet rate example, and I'll just pause it. Okay, so this is our actual correlation test. So it looks a little bit like our Z and our t-tests. So, if you look at the one-tailed, now this is, as I said before, this is the population value row. So again, our sample value, what we're making inference from, is R, and our population value is rho. Looks like that. Now, just to kind of think, the null hypothesis for one-tailed and two-tailed is that the correlation is 0, i.e., we got no, like a little bit like that cloud example we said before. So, if we were to draw a regression line, it'd be almost a straight line, lots of error. And our alternative hypothesis, one-tailed, it'd either be correlation is kind of positive, or correlation is going to be negative, or both could potentially occur. We test for both in a two-tailed test. Now, don't worry about this for the moment. This is if we were building as regression, but generally you can see, we're not going to mathematically prove this, but the t-statistic is a function of R, the sample correlation, and the n we have in the data set. So, remember, R is in fact an effect size. So correlation is, I'll write this out in big letters. We talked about is an effect size. I'll do 4 exclamations, so you want to know. And remember, if you think, this is kind of an equation with sample, but we're kind of like our t is kind of proportional to r root n. So you can see that, as n gets bigger, our t gets kind of, the magnitude of t gets bigger. So it works a lot like the standard t-test. We're not going to prove it mathematically, but again, you've got this combination of an effect size and the sample size n. So that's not exact, but this is the exact formula. And the rejection region is as per our standard t-test, but, and here's the big but, we have n minus 2 degrees of freedom. And why n minus 2? Because when we're doing this, and this is really just a regression test, which we've just kind of called a different name, we've got 2 parameters. We've got the intercept and we have the slope. But even though we're not worried about them for this, we're just worried about the correlation. We do have the intercept and the slope when we make the decisions here. So we've got n degrees of freedom and we lose 2 degrees of freedom. Okay, so this is our example for the tweet rate I showed you on the spreadsheet. And I've got it on the slide, so I'm not going to write it out on my scrawly handwrite. But here we could say, is the tweet rate correlated? And, I would usually say, I might actually put this in the slide, linearly related or linearly correlated. I think linear is probably a better way of doing this. So I might actually put this when I redo the slide. And you could always add, if you were doing a one-tailed, you would add positively or negatively. So we're doing two-tailed. So this is our rho is 0, is our null hypothesis, not equal 0 is the alternative hypothesis. This is the t that I explained before, the test statistic. Okay, so now let's just go back to our data. Yep, I want to keep that. So let's just look at this. So you can remember we have 23 movies, so our n is 23. This is our x, and this is our y. So let's go to new tables. Okay, so I think what we're doing, we're going to do alpha equals 0.05, two-tailed test. So degrees of freedom is going to be n minus 2, which is 23 minus 2 is 21. So our t is going to be 2.08. Okay. So we have a t of, and I obviously calculated this from Excel. So it's going to be a t of 2.08. Keeps coming back to black pen. I prefer red pen when I'm writing on slides. Okay, so 2.08. This was obviously done from Excel. Now remember, we calculated the correlation in Excel as this. This is our n. This is the square root 1 minus the correlation squared. And this gets us, again, this, we obviously know this is a big t statistic. And you can tell on the graph that there's a positive relationship. So there's enough evidence that there is a a correlation between tweets and movie sales. Okay, so just to kind of go back, it's going to ask me to keep my ink. No, we wanted Excel. And you could see here again, SXY is just the sum. And I actually use the alternative formula here. So the SXY equals sigma XY minus sigma X sigma Y over N. So you could play around this and do the two different formulations and see they're equal. So I basically, the correlation, I do sigma XY minus over square root of sigma XX sigma YY. And funnily enough, I do a comparison. Excel has the easy way of doing it. Excel has a correlation function. Again, as I said, it's independent of n, so you just literally pass it the two pieces, the two arrays of data, and then I run that formula for the t-value, and then we find that t-value is significant. Okay, so we're just gonna finish up there, and then I'll do a quick example with SPSS.